And welcome to 6.08. So this is going to sort of be a combination lesson here. We're going to pick up where we left off last week, identifying the effect of algebraic transformations of sinusoidal functions. So looking at, how the different values of the parameters affect the graph of the function. And then what we're going to do is we're going to find the value of the transformation given the graph of a sinusoidal function. So kind of looking at the graph, can we figure out what the function that created it will be? All right, so what you should do now is go back to the app that we were working on, Illustrative Mathematics, and finish out what you were doing. So I would take about a minute to review the part that you've already completed, look at the effects that you saw, and then go ahead and complete whatever you haven't gotten to. There are 2 tables that you want to complete. And what that will allow you to do is kind of think about what does changing the different parameters of your sinusoidal function, what will that do to the graph of the function? How will it change the amplitude, the midline, the period, the phase shift, so on and so forth. And what I want you to do is try and think about the relationship between that particular parameter and the different transformations that may occur. And then what we're going to do is actually figure those out together. So just a reminder of the general form of sinusoidal functions. We have either a sine or a cosine function. Both of these are sinusoidal because we could write either one in terms of the sine. And there are different things that we can do to them. So our input variable is always x, right? And we can multiply the whole sign by some value a. We can multiply inside the argument by b. We can subtract an h value from our input x. And last but not least, we can add something to the overall function. And so the question is, how do these things change the graph of our parent function? So looking at just, the sine of x, how will changing a, for example, how will that change the function? And so for a, it's an easy one to start with. What a will do is it can do 2 things. So the first is that multiplying by some a value will stretch your function. In other words, it's going to increase the maximum and also increase the minimum. And there's an easy way to think about this. The maximum value of sine is 1. So when I multiply it by an a value, say it's 3, the new maximum is now 3. Similarly, the minimum of sine is negative 1. So when I multiply by an a value of, say, 3, I get a new minimum of negative 3. And so the amplitude stretches the function. And so changing the a value is going to create a stretch and determine the amplitude. So the amplitude is going to be equal to the absolute value of a, right? Doesn't matter if I multiply by a negative or a positive out front, the amplitude is going to be determined by the absolute value of a. There's one more possibility, of course, than transformation that occurs thanks to the a value, and that is if we have a negative a value, then we're going to reflect. And it's important to note, what are we reflecting over? So the a value, it turns out, is going, if it's negative, it's going to reflect over the midline. Okay? So if our midline is 0, y equals 0, then it's going to reflect over the x-axis. But if the midline were to be, say, 2, then having a negative would reflect over the line y equals 2. And we'll see this in practice as well. All right, so now let's talk about the b value. And to help us get an idea of what the b value does, it's helpful to go back and maybe play with the slider a little bit in the app that we were working with and see what happens as you change the b value. And what you'll notice is that the b value, as it increases, it compresses the function. So the word that I might be thinking about here when I see the b value is I'm thinking compress. With some of you, I gave the analogy of a slinky. I forget who it was that kind of came up with that, someone in either 2nd or 4th period. But thinking about how a slinky, you can either have it stretched out or you can have it completely compressed. And what the B value does is it allows you to determine how stretched out you want it to be or how compressed you want it to be. In other words, what it does is it makes the minimum or maximum points closer or farther apart. And so what that does is influences the period. And I want to talk a little bit about why that happens. So if you take a look at your unit circle, I'm just going to draw one here. And if you think about it, so on your unit circle, when x is 0, so imagine that you had some b value, maybe a b value of 2. So inside your sign, I'll just write what this would look like. You had sine of 2x. Okay? And so when x is 0, here's where you're at. 2 times 0 is 0, so 0 radians. And then when x is pi over 2, normally you'd be here. And so you'd have sine of pi over 2. But because you're multiplying by 2, your x value of pi over 2 actually takes you all the way halfway around the circle. And so instead of having to use pi over 2, x equals pi over 2 to get to this point, you actually just need half of that, or pi over 4, because you're multiplying by 2. And so what this does is it speeds up how fast you move around your circle. For example, to get all the way around the circle, instead of having 2 pi be your x value, it just needs to be pi, because 2 times pi is 2 pi. And so you're going to get all the way around your circle in half the time than you normally would. And so the b value is going to, the bigger the b value, the smaller the period, right? The bigger you're multiplying, the b value is when you multiply by x, the faster it's going to go around the circle. And so the period is determined by, by the b value, and the period is 2 pi divided by the absolute value of b. And the reason we have the absolute value of b is that it doesn't matter if b is positive or negative. If it were negative, for example, it would just mean that we were rotating clockwise instead of counterclockwise. But for the period, we just care how far apart the maximums are. In other words, how long does it take to go around? It doesn't matter whether it's going clockwise or counterclockwise. Okay, now let's take a look at h. So you've actually seen a situation where we had an h value, and that dictated the phase shift. In other words, a translation left or right. And so we want to decide whether, which way translates it left or right. In other words, shifts it left or right. And to do this, you can go back and look at the app again and cycle through the h value and see what happens. But what I'm going to do is I'm going to give us a little example here. Imagine you had sine of x minus pi over 2. So here my h value is positive. It is positive pi over 2. So I'm subtracting away the positive h value. And notice what this does. When x is 0, instead of being at 0 radians, we're subtracting pi over 2. It cycles me back to this point over here at negative pi over 2. In other words, it delays, so I'll have sine of pi over 2, and I won't actually get to sine of 0 until x is pi over 2. And then I'll have pi over 2 minus pi over 2, which is 0. And so what it does is it moves the initial point of my function. To get sine of 0, I have to scoot to the right to pi over 2. And so if I'm looking at a graph here, and here's pi over 2, notice that sine of 0 doesn't occur. I don't evaluate sine of 0 until I get to this point. So what was originally here at sine, when I just have sine of x, will now shift to the right and be at pi over 2, an x value of pi over 2, thanks to this phase shift. And so I'll be shifting to the right when h is positive. H is positive. And shifting to the left if h is negative. And notice this is not his, this is h is. H is positive. And this dictates what's called the phase shift. So the phase shift, and I'll just use PS to represent phase shift, the phase shift is just equal to h. Okay, and so if I have an h value that is positive, then I'm phase shifting to the right, and if h is negative, then I'm phase shifting to the left. So it's important to know what that means, so the way I would write this is if I had a phase shift, I will take the h value, I'll take the absolute value of it, and I'll say that the phase shift is some number of units either to the right or to the left. That's how I write it. And remember, the way that I decide whether it's right or left is if it's positive, I shift to the right, and if it's negative, then I'm phase shifting to the left. All right, the last one here is the k value, and this is perhaps the easiest for us to understand, because what is going to happen, what transformation is going to happen to my function if I add some number or subtract some number from the entire function? Well, it's going to translate either up or down. And obviously, if it's a positive k value, it's going to translate up, and if it's a negative k value, it's going to translate down. And so what will this have an effect on? Well, if you think about your sine or cosine function, and as you slide it up or down, that's obviously going to affect the maximum and minimum points, meaning that it's going to shift the midline. So the midline is in fact dictated by the k value, and the midline is the line y equals k. So in the examples that we've seen so far, right, if you think just about sine of x and cosine of x, those functions, those have a k value of 0, and that's why the midline is y equals 0. So important to note, if I'm translating up or down, that the midline will also translate up or down, and so my midline is going to be the line y equals k. All right, so now that we have these, and understanding how these parameters transform our functions, it's going to be a lot easier for us to think about how the graphs of these sinusoidal functions should look. So we want to get some practice here. So we're going to sketch a graph of this function. I want you to label the period, midline, amplitude, and phase shift on your graph if you can. So there are a couple ways that we can do this. And I want all of us to start out in the first way. And so the first way is we know how to graph just cosine of x. And so all that's happened to create this new function is that there have been some transformations. So in order to actually figure out how this graph should look, we want to sketch a graph of just cosine of x and then think about the transformations that happen to it so that we can apply those and find the new graph. So before you do anything, sketch a graph of cosine of x on your axis and try and think about what this new function f of x will look like after it's been transformed based off of what cosine of x looks like. All right, so here's cosine of x. I did the best I could to sketch quickly. And now you can go ahead and think about, okay, knowing the different changes that have made, the a value is no longer 1, the k value is no longer 0, how is this going to transform my original function cosine of x now that I know the different parameters here? Now, that might be a little challenging, and so you may still want to create a table of values to evaluate this function and to plot some points. So for example, if I were to plug in 0, then I would have negative 3 times the cosine of 0 plus 1. And cosine of 0 is 1. Negative 3 times 1 is negative 3, plus 1 is negative 2. So the first point that I could plot, when x is 0, the value of my function is at negative 2. So that's, of course, an option as well, and I encourage you to continue using the table if you need to. And if you don't need to use the table, why don't you just think about what the transformations are going to be to your function and see if you can sketch a graph of what the function should look like, and then go through your unit circle and evaluate the values of cosine to see if it makes sense. Okay, so you have a bunch of different ways that you can tackle this, and we'll take a look at it in just a second. All right, so I could keep going through here, and I'll do just one more using the table to help us out a little bit. And if I plug in pi over 2, negative 3 times the cosine of pi over 2 plus 1, and the cosine of pi over 2 is 0, so negative 3 times 0 is 0, plus 1 is just going to be 1. And so I now have at pi over 2 a value of 1. And that's great, and let me just kind of continue doing this in my head. If I plug in value of pi, I'll have negative 3 times the cosine of pi, and the cosine of pi radians is negative 1. And negative 1 times negative 3 is positive 3, plus 1 is going to be positive 4. And so there I am. And if I move around to 3 pi over 2, the cosine there is 0, and so 0 plus 1 is again going to be 1. And at 2 pi, the cosine is 1, and negative 3 times 1 is negative 3, plus 1 is negative 2. And so I can kind of see the basic shape of the function. I'll go ahead and just sketch it quickly. And then I can work backwards as well, and at this point I see the pattern, and so I can just kind of continue it on. And so we have something like that. And if you made the table or you went through point by point, that's perfectly fine, and you'll see that the period, midline, amplitude, and phase shift all fall in line with the transformations that we see here. So you'll notice that we should have a midline of 1, and sure enough, I have a midline of y equals 1. I said that incorrectly, a midline of y equals 1. So there is the midline, and I'll label that. And then I also see that I should have an amplitude of 3, and that means that the distance from the maximum to the midline should be 3, and sure enough, that distance there is 3. And I also see, right, that it should be reflected over the midline, and of course it is, right? Notice that the maximum of cosine usually occurs at the initial value of 0, but since I've reflected it, it's now a minimum. So I have the amplitude and the midline, and now I can think about the phase shift. You notice the phase shift is dictated by the h value. There is no h value there. And the period, the b value is 1, and so the period should also be 2 pi, because 2 pi over 1 is just 2 pi. And sure enough, I see here that the distance between these 2 points is 2 pi, and so the period is 2 pi. And so using what we've just learned about the parameters, I can see that the amplitude is the absolute value of negative 3, which is equal to 3. I can see that the midline is simply going to be the line y equals k, which in this case is 1. The phase shift, there is no phase shift because the h value is 0. And for the period, I have that the period is 2 pi over the b value, which in this case is the absolute value of the b value, which is 1. And so I have just a period of 2 pi. All right, so as we get better and better at this, we're going to work on a method for graphing a function such as this one without having to create a table and without having to graph the parent function first, and really just using the parameters to go ahead and sketch our function. So let's take a look at a few more problems before we are finished. All right, so for each of these functions, find the amplitude, period, midline, and phase shift. Talk just briefly, let's discuss one. So here the amplitude is the absolute value of A, so the amplitude is 3. The midline is the value y equals k, so the line y equals k, so the midline is y equals 0. The period is 2 pi divided by the b value. Notice the b value is what we're multiplying x by, and so we have a period of 2 pi over pi. Pi over pi is 1, so our period is 2. And the phase shift, well, there is none, because there's no h value. H is 0. None. All right, so using this as a baseline, go ahead and complete the second one, and then there's one more problem for us to look at. Okay, so for this function f of x, indicate the amplitude, period, midline, and phase shift. And then go ahead and graph this function together with the parent function sine of x, and use the method which makes the most sense for you. If you still need to make a table, I encourage you to do that only after you've thought about the transformations and tried to just graph it based on the transformations, because we're working towards being able to do that. But then if you need to create a table, feel free to do so.